about material that I already covered, that's okay. Just raise your hand and let me know. But like I said, I'm going to start at 55, okay? All right. So, all right. Cool. Can everybody see the screen? Okay, perfect. So which of the following is an energy diagram for a three-step reaction? B? Okay, why? It has three transition steps. What are the transition steps? The minimums? You sure? Maximums? Yeah. Okay, so which one is it, guys? All right. So that's 1 step, 2 steps, 3 steps. Cool? Okay, and how many intermediates do we have in this reaction? 2. Awesome. So this is I1 and I2. Awesome. All right, what is a transition state? D? Okay, what do you guys think? C? So we just talked about it, right? So what do we say the maximums were? The maximums are transition steps. Yep, exactly. So it's going to be C as in cat. All right? Questions?
Letter D would be intermediate.
I think so. Not one, because it has to like say the minimum, but I think so, yeah. That's okay. All right. Oh, there we go. What is an intermediate? C? Are you sure? Okay, so C. So let's go through all the, what did you say? Okay, so let's look at all of them. So a point on the reaction pathway that has a discrete lifetime. Is that true? It could be A? It could be A. Can it? It actually exists a little bit, right? Yeah. With an intermediate. That's why in SN1 and E1 we can even have rearrangement because we actually form a carbocation. It's not like in an SN2 and an E2 where it's all happening at the same time. So like the intermediate is not actually forming because as you're doing the attack, something is leaving. So which one do you guys think, guys? A? All right.
It doesn't necessarily have to be halfway. That's my thought.
Good point. All right. So 58. Identify the nucleophilic atoms in the following molecule. A? E?
Electron-rich atoms.
Awesome. So electron-rich atoms. Hey, that's a nucleophile. What's an electrophile? Electron deficient. Is everybody good with those two definitions? Anybody need to go over it? No? Okay. So we're looking for the nucleophilic atoms. So which ones are they, guys? Oxygen and nitrogen? It could be. Mm-hmm. Yeah. So that's both B and C. So E as an elephant. Everybody good? All right. So which of the following cannot be an electrophile? A? Did you say A?
Yeah.
Okay, why?
Because the positive sign is on the carbon, so it's a carbon ion, you wouldn't be able to...
But what is the definition of an electrophile?
Oh, never mind. I thought it was the...
Okay. Electron deficient, so anything that can have a positive charge, right? So can that be an electrophile? Can it take electrons? Yeah? Okay. What about B? Are you sure? Okay, so bromine could be a nucleophile, but what about the carbon that's bonded to that bromine? Could that act as an electrophile? All right. What about in C? Oxygen could be a nucleophile, right? But what about the carbon? Could it be an electrophile? Why?
Because the oxygen's withdrawing.
Exactly. So you even have a resonance structure, right? So this can go up here, which gives a positive charge to the carbon, right? Okay, so it could act as an electrophile. Can a negative Br act as an electrophile? Why not? Because it has a negative charge. What do we say an electrophile is? Electron deficient. Awesome. Everybody good with this one? Yeah? Okay. So 60. For the following reaction step, indicate which pattern it belongs to. So what do you guys think? So you guys have been doing these mechanisms, right? The whole semester. So this is just kind of like quick review. Nucleophilic attack, why?
Because the double bond is going to close to electrons are going to oxygen, and that's going to be a carbon ion.
Awesome.
So then the oxygen is going to attack.
The oxygen can attack that carbon. And it's forming a bond, right? So that's the definition of a nucleophilic attack. So, see? Everybody good? All right. So, 61. For the following reaction step, indicate which pattern it belongs to. Rearrangement. Everybody agree? Why? How do you know? Awesome. So, also, what is your other clue other than the fact that you're moving the hydrogen with the electrons?
The charge is more stable.
So you're moving the carbocation, right? So is that, can you have rearrangement when there's no carbocations present? No, right? Okay, cool. So 62. What is wrong with the following mechanism? Awesome. Why?
Because generally with something like a bromine anion, it's a nucleophilic attack, therefore the nucleophile is attacking the carbon.
Awesome. So when we're drawing arrows, guys, where do the arrows have to start? They start at the electrons, and then they point to wherever the electrons are going, right? We're showing the flow of electrons. So everybody good with D? Okay, cool. So 63. Identify the sequence of the steps in the following reaction. Proton transfer? You sure? The first one? Okay. And then loss of a leaving group? Are you sure? Is anything leaving? Are we losing a group? So can that be loss of a leaving group? No. So it's not a loss of leaving group, so we know B is out. We said the first one is a proton transfer, so C is out. Okay, so now we have proton transfer or nucleophilic attack for the second step.
Electrons are going to the positive charge.
Do you have okay. What are you moving?
Oh, another hydrogen. I was looking at the oxygen, so that has to be A.
Right? Proton transfer, 2 proton transfers, right? Everybody good with that one?
Can
Yep.
you explain to me again why is a proton transfer at the second step?
Sure. Okay, so what are our options?
It's either
Like just in general, what are the mechanism arrows that we can use? So we have nucleophilic attack, we have loss of a leaving group, proton transfer, and a rearrangement. Arrangement. There we go. Okay. Can it be loss of a leaving group? No. Okay, so we know loss of a leaving group is out. Can it be a rearrangement? Why not? Right, right. That's your first hint. Rearrangement occurs when we're trying to form a more stable carbocation, right? When we're trying to go like from a secondary carbocation to a third carbocation. That's not what's happening here. So that one's out. So now we have between a nucleophilic attack and a proton transfer. So which one do you guys think it is? Which one can you guys take out?
right. It's just because of
Right. I know it's a little weird, but we know for sure it's not a nucleophilic attack.
Yeah.
Okay, cool. That's okay. So proton transfer. Everybody good? All right. So 64. Identify the sequence of steps in the following reaction.
Talk about this one a little more as well. So your pelvic diaphragm or your pelvic floor, I write floor here so we can remember, it's the same thing, is made up of the levator ani muscle, which has 3 parts, plus the coccygeus, which is also the ischio-coccygeus, same thing, slash. Okay? So we need to know the 3 parts of levator ani, because you might be asked which of the following muscles does not help form the levator ani, right? So we need to know both parts of that, or he might not write this, but he might write all of its parts, so we don't want to miss a question just for that. So the 3 parts of the levator ani are the puborectalis muscle, and this one is key for fetal continence. So this is the main muscle responsible for that. You also have pubococcygeus, and then you have iliococcygeus. So remember, this is kind of a tricky one. Ilio is part of levator ani. I remember it because of L, so L and L, and ischio is its own thing. So I think that's a pretty easy point to kind of like mix up on your head on the test. Cool. Something else I was going to write. I'm going to continue this down here a little bit. In males, this attaches to the wall of the prostate. Okay? So then we call that levator prostate, like this, E at the end. So it attaches to the wall of the prostate. I'm not going to write that out, but y'all know. In females, it attaches to the urethra and the vagina, and that's called pubo.
All right, so, and we said it's a heptane. All right, so what are we going to name this? Awesome, okay, good job. So we also have chirality. So what is this? What is the configuration of this chiral center? S? Everybody see it, or does anybody need me to go over it? Chirality. Right, awesome, yep, good point. So this is 1, 2, 3, and we know we have a hydrogen in the back, right? 4. So this gives us R, but our lowest priority is on a what? It's on a wedge, so what do we have to do? Flip it, right? So this is S. So we have S, 4,5-dimethyl, what else? Oh, thanks. So S, what is it? 2-bromo, 4,5 dimethyl heptane. So that gives us what? B? Right? Cool.
Question, because on the test I did the same thing when they're unwedged. I did it, normally, and then I will just flip it. And then I got some of them wrong. And he showed me a technique where you just have to write, put the numbers, and then from that you have to flip it or something. Like, it wasn't right if we just flipped it and we did it backwards. So I don't know if there's a special occasion.
You have to make sure. Why do we have to? That's a good question. Why do we have to flip this one? What was on the wedge? The lowest priority. If the lowest priority is not on a wedge or a dash, can we use our rule? No. What do we have to do then? Right, swap the groups. So maybe that's what you're talking about. When the you only have to look at where the lowest priority is. So if your lowest priority is on a dash, what do? So your lowest priority is on a dash. What do you do to the configuration once you figure it out? Do you keep it or flip it? Keep it, okay. If it's on a wedge, what do? And what is the special situation with this? When it's not on a nor on a wedge or a dash, right? So if it's on neither, then you have to switch the groups. Right? Does that make sense? If we have time, maybe we can do a problem like that.
I know how to do it. It's just that I didn't remember that.
Yeah, exactly. Because those, yeah. Everybody good with this, guys? All right. So now 66. How many primary carbons are in the following compound? Two or three. Okay. How did you guys figure out how many there were? A carbon that's only attached to one. So is this a primary carbon? So are any of these in the benzene ring a primary carbon? Okay. Is this a primary? This one? This one? This one? This one? This one? All right, so that's two. This one? 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 Yeah? Okay. So what is it, guys? Three. Okay. So I know some of these are some of the questions that sometimes you have to do is just a matter of taking the time to go one by one. I know sometimes it's a little tedious. Yeah, but those are easy points that you can get. You know what I mean? The way that I see it, when I'm taking tests, is that if I know I'm really slow on a problem and I know how to do it, I'll still just skip it because I want to go back when I have time. How long did it take us, even though we went carbon by carbon? Maybe 20, 30 seconds at the most. And it's pretty easy points that you can get that you don't have to miss, right? So always try to get what it's easy, quick, and then you can go back. Even if you know a concept, you can still go back later, right? Especially if you know you're a little bit slower at doing those problems, right? All right, 67. Which of the following is a reasonable definition of a concerted reaction? C. So it is a reaction in which all bond breaking and bond forming occurs at the same time. Everybody agree? So, okay, cool. So that can be an SN2. What else can this be, guys? E2? Awesome. All right. So which of the following is not a possible step in a substitution reaction? So this is just kind of mechanisms, right? So I heard C. D or B? D? Okay. Why? So who said C? Okay, why C?
Unless we just assume that there's some sort of reagent, you can't just have the bromine leave on its own.
Are you sure?
I mean, it's a good leaving group, but it can't just leave like that.
Always? Are you sure? What about in an SN1? In an SN1, what is the mechanism of an SN1? Bromine leave on its own, and then you have a nucleophilic attack. So you can have a leaving group leave on its own, right? Okay.
Primary carbocation for D, that's why.
Okay. Good point. Yeah. Well.
Because of an addition reaction.
Awesome, right? So in here, if we look at D, this looks like one of the steps in one of our addition reactions. And that's not a substitution, it's addition, right? All right. And this could be part of an SN1. This could be a step of a substitution reaction, right? Because all we're doing is first protonating the OH to, why do we protonate it? Awesome. So this makes it a good leaving group. What about A? What kind of reaction is that? SN2. Awesome. Everybody good with these? Did you have a question? Yeah.
So, if there's a double bond and something, it's pretty much, it's just addition.
So that's a good question. So When we're substituting, what are we doing? Like, what is the overall like idea of the reaction? We're replacing one group with another, substitution, right? What do we do with elimination? You're creating a pi bond. Cool. What do you do with addition? You're breaking a pi bond, and you're adding two groups to the alkene. Cool. What other reactions do we have? If I do a double elimination, what will I get? A what? Alkyne. Awesome. I'm sure there's more, but I can't think of any at the top of my head right now. But yeah. So D, that's like you said, that's an addition, right? We have an alkene. We're breaking that alkene, and we're adding two groups on the side. That's just part of the mechanism, but it's not the whole mechanism. So just take a look at those mechanisms and remember your reactions. Because sometimes, even if you don't necessarily remember your reagents and you're not sure what the product is going to look like, if you know the mechanisms, you can come up with the product, right? You can always draw the mechanism and just see what the product's going to be. Okay? All right, 69. Which of the following is a product of the following SN2 reaction? What is it? D? B? Okay. C? One of those two? All right. So let's look. So what kind, we said that this is an SN2 reaction, so what's going to happen? It's going to happen all at once. What's going to happen all at once? Okay, so a strong nucleophile is going to attack, do a nucleophilic attack, and the bromine is going to do what?
It's going to leave.
It's going to leave. Awesome. It's C? Okay.
Because the oxygen go to the secondary carbon.
Awesome. Okay, everybody good with this one? D? We can do it. So let's count the carbons, right? I always say count your carbons. This is how you can avoid silly mistakes. Because sometimes you get the hardest thing done, and then you mess up when you count the carbons, and you put an extra carbon in there, and you still get the answer wrong. And that's a silly mistake to have, right? Yeah. Okay, that's a good point. So let's look at both of them. Okay. All right. So let's attack first. So it's going to attack here. What kind of attack is this? Backsided? Awesome. So what did you say we were going to have? Inversion. Awesome. So it's going to be inversion. Okay. So let's count the carbons. We have 1, 2, 3, 4. So when I form the ring, I have to make sure there's only 4 carbons in like that whole ring, right? So I have my oxygen that acted as a nucleophile, and then I have 4 carbons. So 1, 2, 3, 4. So we know like it's forming this ring. And then we have a methyl group, and that methyl group is on my 4th group. So let's just number 1, 2, 3, 4. So I know I'm going to have a methyl here. Everybody see that? And that's where my 5th carbon is coming in here. All right? Does that make sense? Everybody good? All right. So now let's look. So my BR was on a wedge. Where is my H? On a dash. So when I close this, we said we're going to have inversion, right? So if so I know with a ring it's a little harder to see the inversion because like it does like in a weird thing, but in this case the methyl is gonna be on the wedge. Yep. I know it's like kind of weird like to see with a ring, but if you're not sure or if you're professional, it's because it's like when it closes it's a ring, and like just because the BR is on a leaving group, I mean the BR is on a wedge. It's kind of hard to explain just because it's a ring. I would just go to your office hours, like with your professors, if they still have office hours, and tell them to explain this one to you. But just remember, with an SN2, what do you have? Inversion. I don't think they're going to give you one like this, though, to be honest. Yeah. So in this case, remember, the methyl is on a line. Right, it's on the plane. So that's why like when you rotate it, and I'm really bad at like rotating groups. So that's why like it's really hard to explain why. But just go to your professor's office hours. They can like go over that. And like if they tell you otherwise, just go by what your professor says. But this one is C. It's not A. And remember, this methyl is not on a wedge or a dash, so that's why it's harder to see. It's on the plane. So when we have inversion, it like pops it to the other side. Okay? Okay, so 70. Rank the following substrates from most to least reactive in an SN2 reaction. So again, what kind of attack do we have with an SN2 reaction? Backsided attack. So what do you need for that? What kind of substrates? Primary? Okay. More reactive than what? Tertiary? What's in here? What's in the middle? Okay, secondary. Oh, also, just before I forget, if you guys have like a little bit of trouble with SN1, SN2, E1, and E2, and looking at the competition, like what's happening, which one favors what, if you guys go to ucfsi.wordpress.com, I have not taken any of my worksheets down. I think this was on exam 2 for Dr. Dowdy. So if you go to like exam 2 material, there's going to be links there for some PDFs that can help you see. Like it just pretty much organizes all the information and tells you SN2 is favored by this, SN1 is favored by this, E1 versus E2. So if you guys just need a refresher, I have that worksheet there, so it's very helpful. I got that worksheet from my SI leader when I took Argo 1, and it really helped me, so I really, really, really recommend. And I have other worksheets on my website as well. So, and like I said, I haven't taken anything down, so everything from exam 1 is on there. So that can be a good refresher. All right? So which one is the most reactive here? Methyl. So this is 1. What's my second one? C. Third? B. And fourth? D. Yes. But you won't form the intermediate because it's an SN2. So you won't form the carbocation, right?
It doesn't react at all. It doesn't react.
Right, awesome. So what is this one, guys? So this is C. Between what? Between which ones?
I was saying, what's the difference between B and D? Because I thought they were both.
This is an aryl group. So because like this is directly coming off of the benzene ring, that's what's even less reactive. Everybody good with that? All right, cool. So 71. Rank the following substrates from most to least reactive in an SN2 reaction. So what are we looking at here, guys? So right, so we have different leaving groups now. So what is usually the trend for leaving group? Down the periodic table is what? Is it a better leaving group or a worse leaving group? Better leaving group? Everybody good with that? Okay, so now that we know that, between CL, I, and BR, which one is the best leaving group? I? Everybody good with that? Oh. What's the second best leaving group? BR. Okay, so now we just have to pick between A and B, right? Because they're both the same leaving group. So which one is a better leaving group? Well, they're both CLs without the double bond. Okay, cool. So 3, 4. So CDBA. So B? Yep. Everybody good? All right. So 72. Rank the following substrates from most to least reactive in an SN1 reaction.
The opposite trend of that.
Opposite trend of SN2. So what is that? No. Aryl group is still bad.
I thought it was the opposite, like exactly opposite. That was last in the SN2.
Aryl is like just bad for in general.
So then tertiary is favorite.
So tertiary is favored over what? Over what? Over what? Over methyl. And do we have anything that's more reactive than tertiary? Allylic, awesome. And what's more reactive than allylic? Vinylic? Are you sure? That's worse, right? Which one is better than allylic? Benzylic, awesome. But it's different though. That's a good question. This is why I brought it up. Before we get into that, why do we notice this trend with an SN1 reaction? Awesome, because in an SN1 we're forming a carbocation. So when you form that carbocation, you want like the most stable carbocation that you can have, right? Okay, cool. So let's talk about benzylic and aryl for like 1 second. I know. It's just like a matter of recognizing positions. Okay, which one is which in this case? Yeah. Benzylic. And this is an arrow. And before we get into this one, let's do allylic and vinylic real quick. And then maybe this one will help you out a little bit more. So, which one is allylic? The top one. And vinylic? Awesome. Which one is more stable? Awesome. Awesome. Because of resonance? Because of resonance. So this is really unstable. Cool. So what will the resonance structure look here? Awesome. You guys are going to do great. Do I have resonance structure here? Right? So you see the difference in positions, right? The allylic position is 1 away from the carbon. Vinylic is right on the carbon that's participating in the double bond. Does that make sense to everybody? All right. So now let's look at benzylic and arylic. Right? Benzylic, once this leaves my carbocation, it's going to look like this. Kidding, this goes away. Can that be stabilized? How? Resonance, right? We can do the same thing. We can resonance, and then this can move, and then this can move. So it's like really, really, really stable, even more stable than allylic, right? But what about this one? Once this leaves, my carbocation is on the double bond. Awesome, so it's kind of stuck there. We can't really do anything to stabilize it. And it's, what kind of hybridization is the carbocation on? sp2? Yeah. Everybody good with this now? That's a good question. So we said for SN1 and E1, what do we form? Carbocations. So if we form a vinylic carbocation, how stable is that? So will it want to do the reaction? We need a stable carbocation, right? The more stable the carbocation, the more likely it's going to do SN1 or E1. That's why we like benzylic, allylic, tertiary, secondary, primary. That's why we see that order. Everybody good with that?
You don't want a carbon that has a positive charge and has a double bond with the carbon.
Not necessarily, because if you have an allylic carbocation, that's stable.
I know, but the plus charge isn't on the...
Right, exactly. Yeah, but like, because what I heard was if you have a double bond and a positive charge, it's going to be unstable. But it just depends on the position that it's at, right? On the carbon, not stable. 1 away, very stable. Everybody good with that? All right. So now if we go back to this one, leaving group is the same, so we don't even have to look at the trend, right? Because they're all I. So we just got to look at what kind of substrate it is. So which one is going to be the most stable? A. Then what? B. Then what? Then what? So that is A. Everybody good with that? All right, cool. 73. Which of the following is the major product for the following SN1 reaction? Oh, yeah, it's there. So who tried the review already before you guys got here? Okay, so one person. Oh, you did too? So. All right, so I'll give you guys like 2 minutes. Try to get the reaction done, and then tell me what you come up with. Okay? So I'll give you guys until like 11:08 or so. might want it, others might not. So that's a good question to ask your professor. Okay? All right. So 74. What type of solvent would be best for obtaining an optically active product in the following reaction? Okay, so let's talk about this. Let's start with this. What does optically active mean? It's a chiral molecule, right? Awesome. So in order to be optically active, I need what do I have? SN2 or SN1. Awesome. Awesome, yes. So we have SN2 or SN1. Which one out of SN1 or SN2 will give you a racemic mixture? SN1. And we said racemic is optically inactive, right? So can it be an SN1? What do I get in SN2? Inversion? Awesome. So I know that I need to do some kind of SN2 reaction. Okay, so now it says what type of solvent would be best. So what type of solvent favors an SN2 reaction? Aprotic. So B? Right? Everybody good with this one? Okay, cool. So which of the following is the correct IUPAC name for the following compound? B? Everybody agree? Yeah? Anybody need me to go over it? How come we can't use cis or trans here?
There's no dash.
Are you sure that's why?
Oh, also like, yeah, there's no. Yeah.
Awesome. One side has the same groups, methyl and a methyl. Can I use E or Z for this one?
Yeah, you can use it.
Why?
Yours is the only one is there's chirality, right? Or trans, alkene, whatever.
Okay, so that's a good question. So we have cis and trans, or E and Z. When do we use cis or trans? When there's, to compare the same groups. Compare the same groups. And they have to be across the alkene, right? Not on the same side. So in this case, we have two methyls on the same side. Can't really use either one. E or Z, what are we comparing? Awesome. So it's 4 different groups when you don't have 2 of the same groups. Awesome? I mean, cool? Everybody good? All right. So we're going to, when we have 4 different groups. Okay. And they're both for alkenes. Right? So in this case, we have 2 methyls on one side of the alkene. So we can't really use either one to compare them. Cool? Everybody good with this? Okay. We're going to practice it. Don't worry. Let's do 76. So I'll give you guys like 2 minutes. Name it real quick and tell me what you came up with. D, C, okay. So I'll give you another minute, okay. D? All right, everybody agree? Anybody need me to go over it? Yeah? Okay. So we said it's D. So why? Okay, so longest carbon chain with my double bond. So is that the one that you guys got? Yeah. Okay, so that's a heptene. Now, where did you start, on the left or on the right? From the right. Why? Okay, so we're going to start on the right. Okay, so then we named the substituents. So we said 3-methyl, 4-methyl, 5-methyl. Okay, cool. So then what did you guys do? What do we have to take into account for this molecule? Chirality. Okay, so we have a chiral center. So you guys got R? Okay, anybody need me to do that one? Yeah.
So for R, you're only looking at that 5
Good question.
For the E and C, you only look at the double bond.
Good question. So we assign configuration to the chiral centers. So if you have more than one chiral center, you have to do the configuration for all the chiral centers, right? And you'll have to indicate 2R, 3S, 5R, whatever, however many chiral centers you have. And then for the ESZ or cis and trans, what are we looking at? The alkene. Cool. So you guys got E in here. So why? Okay, so good question. So is trans and E the same thing?
No.
They're not the same thing. Okay.
E just means opposite, right?
E does mean opposite, but just because they're on, you have to figure out what is on the opposite sides. Because we do priority for E and Z. Cool. This one is kind of easy-ish to see it. But remember, E and Z are not the same as cis and trans. You can have something that's cis and it's E. Or you can have something that's trans and it's Z. Right? We're gonna do it right now. So when we're doing E or Z, how do we determine what it is? How do we start? Assigning priority. How do we assign priority? Same for chirality, right? With atomic number. Okay. So we're looking at everything that's on this side of the alkene. I'm going to do it here because it's getting messy. So I'm looking at this side of the alkene and at this side of the alkene. So first I'm going to see which one is a higher priority on this side. So which one is a higher priority? The one in the bottom. So this is my high priority and this is my low priority. And on this one, which one is my high priority? Up. And which one is my low priority? Methyl. So I'm comparing my high priorities, right? So I'm comparing high and high. What side are they on, relative to each other? Opposite. So what is that? E. Could I have also used cis or trans for this one? Yeah, why? further. So we're going to look at what's bonded to this carbon and what's bonded to this carbon. What's bonded to this carbon? Oxygen, and what else? Hydrogen, and what else? What's bonded to this carbon? 2 hydrogens? 2 hydrogens and an oxygen, right? Does everybody see that? Okay. What's bonded to this carbon? 2 oxygens and a hydrogen, no? Because that's 1, 2, 3, so I know that there's an H here, and there's 2 here. Which one has a higher priority? The bottom one? High, and this is low. So which one are we picking? E? Does everybody see that? Okay. And you guys get how we broke the tie, right? We go one by one until you break the tie. So this oxygens are the same, so we can't use that one. So we move to the next one. Now between this oxygen and this hydrogen, obviously oxygen wins. So that's why we have E. Everybody good with that? For this carbon? So what's bonded? Okay. Everybody see it? Everybody good with this? Questions? You sure? All right. So let's do the next one. So this says from most stable to least stable. So how do we figure out the stability of alkenes?
The number of substituents.
So the number of groups, R groups, or substituents? Okay. Okay. So which one is my most stable one here? B. Which is more stable than what? C. Which is more stable than what? Awesome. Di? Are you sure? Why? Awesome, right? So we're looking at like everything on each side. So that's 1, 2, 3, and 4. Everybody good? All right. If I was to give you one like this, which one is more stable? Awesome. Good job, guys. You're going to do great on the exam. Just know it. All right. Huh? Which of the following alkyl halides would afford the indicated product upon reaction with sodium methoxide? Awesome. So we said it's this product, right? We said it's with sodium methoxide, and it's telling us where do we make that from?
Oh, we have to use synthesis in vitro.
Kind of, a little bit. But we're going one step back. We're just trying to see which one is going to give us that product. We do. So you're forming a double bond. So what is this acting as? A nucleophile or a base?
Elimination.
It's elimination, so it's a base? Okay, cool. So we're saying this is an elimination. What kind of elimination is it?
It's
E2? Why? It's strong. Awesome. So strong, non-bulky. Okay. So what product is usually going to be favored with a strong, non-bulky base? Close. Your head is in the right area. So what kind of products can we have with an alkene? Zaitsev, Hoffman, do you guys remember that? A little bit?
It's
Zaitsev, why is it Zaitsev?
the only time where it's not Zaitsev is when there's a bulky base.
Awesome. Okay, so in this case, we're going to favor Zaitsev. What does that mean, Zaitsev? Most substituted? Awesome. All right. So now that we remember all that, let's look. We're saying that it's we're making a double bond and we're trying to see like where it came from, right? All right. So can we take out any of these? Can it come from C? Why not? Awesome. There's no proton here that's going to form the double bond here. You can form a double bond here, but is that where our double bond is? So this one's out. Do I have anything else that's out? Why? Well, so you have a good leaving group, but just look at what kind of like product you will form, right? In this case, ucf.wordpress.com. In here, you just go to, obviously, Organic Chemistry 1 with Karina. If you go in there, I have a worksheet. It's going to be under exam 2 materials. And it's just going to be a PDF of like a paper that is like SN1, SN2, E1, and E2, and what favors everything. Strong base versus weak base versus strong nucleophile versus weak nucleophile, primary, tertiary, like all that stuff. It's just like a really helpful, like a way to organize it. Okay? All right. So we said E2 because this is a strong base. So we said it's concerted. And we said, is this a bulky base or non-bulky? Non-bulky. So what does that tell us in terms of the product? Zaitsev? So if it's a non-bulky base, it favors what kind of product? Zaitsev. What does Zaitsev mean? More substituted. And if it's a bulky base, and then it favors what? Hoffman. And what is the Hoffman product? Least substituted? Huh? Yeah. Okay. All right. So we said strong base, concerted, non-bulky, so it's going to be Zaitsev. So can we take out any of these? A and B. What kind of products are those? Hoffman. Awesome. Okay. So why do we take out A and B, guys?
It's about the double bond.
Yeah, exactly. This is the Hoffman, right? The double bond is the least substituted. But we said we need the Zaitsev, which is the more substituted. So it's going to be C or D. Everybody good with that? All right, so now how do we pick between C and D? Stability? Okay, so let's talk about this. So if we said this is an E2 reaction, this is my base. What is that base going to do? It's going to what? Deprotonate. And it's going to be this beta proton, right? How many beta protons do I have? So what do we have to do every time we have only one beta proton to deprotonate in an E2 reaction? Newman projection to make sure that they're anti. I know. Do you guys want me to draw it? Okay. So let's do this again. So BR. Okay. So we say we have to draw the Newman projection. So where do you guys want to like look at it from? Here or here? The BR? Okay, so we'll do here. So that's my front carbon. So what's on my front carbon? Okay, and what's going where? Are you sure? My hydrogen is on a wedge. Left? All right. Okay, we can do that. I'm going to come up here for a second. I don't want to be the camera. All right. So if we're looking at, this is my molecule, right? This is my molecule. If something is on a wedge, it's going to be coming out of the paper, right? So my pen is my wedge. So if I'm looking at it from this side, and it's on a wedge, what side is that on? Like, related to me? Left or right? Right. If I go to the other side, does it switch whether it's on a wedge or a dash? Still on a wedge, right? It's just like the only thing that's changing is where I'm looking at the molecule from. So if I'm looking at it from this side, is my pen on my left or my right? Left. So wedges don't always mean like left or right. or dashes don't mean always left or always right. They just mean out or in, and it just depends where you're looking at it from. Okay, so what if it was a dash? If it was a dash, it's going where? In or out of my paper? Behind, into my paper, whatever helps you out. So it's going to be here, right? So it's going to look like this, and that's kind of hard to see. So if it's going into my paper, is it on my left or my right? What is it? My right? But if I was looking at it from here, it's still a dash. So is it on my left or my right? Left. Make sense? Okay, cool. Did that answer your question? Okay. So let's go over here. So my eye is here, right? And if it helps you, you can always, like, something I used to do when I used to take the test is like, this is my molecules, and I'm looking at it from here. And like that always helps me. And like if my eye was on the other side, I would just look at it from the other side. Yeah, so. So hydrogen on the left. So what's going to my right? Bromine. What's going to up top? Methyl. And then if I do my circle, what's on my right, left, and bottom?
Right is hydrogen, left is methyl, bottom is methyl.
So is my leaving group and my proton anti to each other? Okay, so I have to rotate it. You guys want to rotate the front or the back?
Wait, so what do we want? We want the Br and the H to be anti?
Your beta proton and your leaving group, they have to be anti to each other. So what am I rotating? Back? Okay.
Oh, is it because the beta proton is on the back carbon?
In this case, yes. Because this is my beta proton. And I'm looking at it from here. My beta proton is here, my leaving group is here. And when I drew the Newman projection, the BR is...
H on the carbon that is also attached to the bromine, that's the alpha proton?
Good question. Possibly, not sure to be honest. But this is the alpha position, so possibly, maybe. All right, so let's rotate the back. You guys want to rotate it clockwise or counterclockwise? So we have H, ethyl, and methyl. So now they are anti to each other, right? So now I can eliminate. We get rid of this. We get rid of that. So now I just have to draw what double bond I have. So I have my double bond, my front carbon, which is double bonded to my back carbon, right? Because the double bond is between this front carbon and my back carbon. So what's coming up to the top of the double bond? Methyl. And what's going to the bottom? Hydrogen. And then on my back carbon, what's going to the top? Ethyl. And what's going to the bottom? Methyl. So I'm going to have So which one is it, guys? Are they cis or trans to each other? Which one is trans out of these ones? C. Everybody good? If you only have one beta proton, yes. Because you just have to make sure that they anti. You don't have to worry about it. All you pick is that you have to pick whether it's Zaitsev or Hoffman first, and cis or trans, which we said trans is usually more stable, so you're going to go with trans.
But with 2 beta, it's always going to be trans, and it's more stable.
That's a good question. I don't know if the book says it like that, to be honest. Like, I know we're trying to come up with shortcuts, but I don't know, if that's... Huh? Yeah, that's what I like to do because, drawing it out, it just helps you see what's going on. So, you have less of a chance of getting it wrong, as opposed to oh, it's a trick, but you're not really sure if that's the way.
If we have 2 beta protons, we don't have to draw. So
No.
how would you tell by just looking at
Just trans. Just make sure it's trans at least. Or like, and then you have to pick whether it's Zaitsev or Hoffman. And you have to just look at the base. That's what I would do at least. Yeah. Did you guys have any other questions?
Yeah, so it's C because it's trans and we want a more stable product, right?
In this case, we did C because we did the Newman projection, and that's what the product was. Yeah. All right. So 81. So which of the following shows a mechanism for a concerted elimination? A? What kind of mechanism is that? E2. Awesome. So what's happening in an E2 mechanism? Somebody just like summarize it really quick for me. Concerted. But like, what is the mechanism? Okay, a base deprotonates a beta proton. You pick which one depending on the base, and the leaving group leaves. And what do you form? An alkene, a pi bond. Cool. Everybody good with that one? Yes? Yes, it's A. D. Okay, good question. What do you have here? A carbocation. Can you have a carbocation in a concerted mechanism? So what? That's part of a what? E1.
So B, C, and D are all out just because of that.
Because you have intermediates. Remember, in an E2, it's all concerted, right? Does that make sense? Some of these questions, guys, I don't see like you're like saying like, oh, like make it super simple. Some of these questions I put it so that you guys can review these mechanisms, right? Because we don't have time to go through all the mechanisms that you've learned the whole semester, but at least just like kind of like recognize them and make sure that you're understanding everything in each mechanism, and then that's going to help you when you're doing reactions. Everybody good? All right. So 82. What would be the best base for performing the following elimination? D? Awesome. So we said it's a bulky base. So what kind of product is this? Hoffman. Huh?
The one that we just did was Zaitsev and it was NaOMe.
Right, and that's a small non-bulky base, right? Okay, cool.
Sodium terbutoxide is a bulky base.
Sodium terbutoxide is a bulky base. Awesome.
I know, but why is it not A? I picked A.
It's just that the product.
Remember A, and this one is a small, and this is what we got. We use a small.
Zaitsev product?
Zaitsev is more substituted, but we want less, we make it small. And this is Zaitsev. But here,
Okay.
you look at it, it's on the end, right? That's awesome. So you can
What? We're gonna go over this right now. So when we have an E2 mechanism, we have two different kind of products that we can have. What are they? Zaitsev and Hoffman. Which one favors Zaitsev? Small, non-bulky. Which one favors Hoffman? Bulky. And what is the definition of a Hoffman? Less substituted. Less substituted. And what is a Zaitsev? More substituted. Okay, so now let's look at our substrate. So this is our alpha position, right? So this is where the leaving group is going to go. So from here, we have two choices. We have these beta protons, and then we have one here, right? And in this case, they gave us the reaction already. Which one got deprotonated? The one on the left or on the right? On the right, which gave us the least substituted product. So that's the Hoffman, right? So if we need the Hoffman product, what kind of base do we need? Bulky base. Out of all of these, which one is the only bulky base that we have? Sodium terbutoxide. Did that?
Yeah, that answer.
Okay. Cool. Everybody good with that? All right. So what is the product of the following elimination? So it's not A. Why is it not A? Okay. Cool. It's not B. Why? Same reason. Too many carbons away. Cool. So we have C, D, or E. So which one is it going to be, guys? Yeah. What do we know in a chair conformation? What do we know about the leaving group and the hydrogens have to be? Axial, yes. And what else? What's the other word? Antiperiplanar. Right? So what do we have to do for this problem? Chair conformation. Awesome, exactly. Because with that cyclohexane and we do the chair conformations, we have axial and equatorial positions. And when we're doing E2 eliminations, they have to be axial and antiperiplanar. Awesome. Okay. So let's do 83. Okay. Okay, so now I'm going to draw the chair conformation, right? So how do you guys want to do it? What do you guys want to start on this? CL? And go counterclockwise or clockwise? Okay. So when we're doing chair conformations, wedges mean what? Down? You sure? Wedges mean up? And dashes mean down. Okay. So my chlorine is on a wedge, and it's on position 1. So if I go to my chair conformation here, position 1 is what? Axial or equatorial? Are you sure? In that position, it's up, so it's equatorial. Awesome. It depends on how you draw it. The way that I drew my chair like this is equatorial, but once we flip it, that can change, right? Exactly. All right. So my leaving group here is going to be equatorial. And my methyl, that's down. So is that axial or equatorial? Are you sure? Are you sure? It's down. So in this position, it's down equatorial or axial? Do you guys remember your positions?
Yeah. I just remember, like, remembering with the chair, it's like whatever, like, if it goes from, like, it's slanting down, the axial is going to be, like, straight down.
Awesome.
And if it's tilted up, the axial is going to be straight up.
Awesome. That's a good trick. I like that. What was your question, Leah?
How do you know where to start, which carbon to start with? As long as the chlorine and the methyls are a distance away, are one carbon away from each other, that's fine.
Oh, like you mean like where you start counting? You can start counting anywhere.
I know, but like, as long as the chlorine and the methyl are like one away from each other.
You just have to make sure that they're on the same number carbon that they are. So you could start one from here.
What I'm saying is like you may not have equatorial chlorine if you start from a different start angle, you know?
Yeah, exactly. So like that's what I'm saying. Like it just depends on where you start and where the groups are at. Where you number it.
So then I guess it doesn't matter if it's equatorial or.
It does matter. Right now it's equatorial.
In this case, but what if you put chlorine on like.
You could rotate each number 1 spot, so like that middle part that's the up part, you could put your number 1 there instead of number 2, and you could put the 2 on the down, just where you number it, but then like based on where you number it, then the legend dashes matter.
It matters on where you number it.
So you can pick your numbers, but once you pick your numbers, you have to commit
Exactly.
those numbers,
Yes.
and then put your wedges and dashes based on the numbers that you pick.
Thank you.
Yeah, but what I'm saying is like chlorine's not going to be equatorial like that on every single carbon.
Right. Yeah.
So So
No,
like,
every carbon has a different position. Every carbon has an equatorial and an axial.
But like the rest of them, we don't need to label it since it doesn't have any substituents, right?
I just do because I'm just used to it.
Okay.
Like
How
if,
would you know up or down?
okay, let's do this, guys, real quick. All right, let's do a chair real quick. So, when we have a chair, Leo, this might answer your question. Right? We have this chair, or we have the other chair when it flips. Cool? Okay. What he was saying is like once you number it, you have to commit to the numbering. Like do it the same way. You know, you can number however you choose to. Like you can start one at the bottom, you can start one at the top, one on the right, one on the left. In this case, it doesn't matter, but you just have to commit to it because you can't change the numbers depending on what's convenient to you because then you're going to mess up. Does that make sense? Okay. So when I've done chair conformations, I have always just started on this side. There's no reason why. I just did it that way and I've stuck to it for all these years. Okay. So I just start 1, 2, 3, 4, 5, 6. And remember, when you have a ring flip, what happens in the ring flip? Awesome. The corners are just going to like go to the other side, right? So this is going to go up here, and this is going to go down here. Cool? It doesn't matter. This is just how I number them. Okay. So if I did that, where's my position 1 now? Up, right? Now I'm starting here. Cool. All right. Everybody good so far?
does the numbering not matter too? Like you number.
It doesn't matter. You just have to pick and stick to it. Yep. Just make sure that you're numbering correctly. And when you do the chair flip, just make sure you're like moving the numbers correctly. You can get to. I see some people that start the 1 on this side. I see people that start the 1 here. It doesn't matter. Just make sure you stick to it. I personally just started here because I like doing it like that. It makes it easier for me. Okay. So in this position 1, there's an axial and an equatorial. Which one is up? Are you sure? Axial down. Awesome. So the good way to like remember, axial just means like straight, right?
I drew it different.
Okay, yeah, no, and that's okay. Yes, exactly. Like one hint is like this carbon is kind of like pointing down. So your axial is going to be pointing down. Does that make sense?
Yeah.
That's a good
I
way.
just do a different way than you did.
Which is okay. And like I said, like whatever way you have been doing chair conformations, don't change it at this point for me because like it's going to confuse you. Like this is just the way that it works for me. But whatever way you learn, either from your professor or from the book, whatever you've been doing this whole time, stick to it. Don't change it now. Okay, so this is axial. So now in position 2, if this is axial down, what is going to be position 2 in this case? My axial, is that going to be up or down? If in 1, my axial is down, what is 2? What is 3? What is 4? What is 5? What is 6? So they go back and forth, right? Okay. So if my axial is down here, what does my equatorial have to be here? Cool. 2? And what kind, equatorial or axial? Awesome. So it's all going to be equatorial. So what is this, up or down? And this one? And this one? And this one? Does that make sense to everybody? Okay. Now when we flip the ring, what happens when I flip the ring? Everything switches. Awesome. So now my axial here is going to be what? Up. And here, down. And here? 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 And my equatorial is going to be what? And this one? This one? This one? This one? And this one? Up. Awesome. Does that make sense, guys? You guys remember this now?
I just wanted to ask you before going like over. And this one, we're trying to just put the methyl going down because it's undashed, which means that it's going down.
Exactly.
There's two should be axial, right? Now the chlorine and the methyl should both be axial. One is up
Okay,
and down.
so let's look at it now. Now that we like went over that real quick, right? In this case, the way that I started the numbering, I started my 1 at the chlorine. And in this case, my chlorine is up. So in my position 1, the way that I drew my chair, up is equatorial, right? Okay, cool. But when we do eliminations, what position did they have to be, guys? Axial. So what do I have to do to switch it to an axial position? Do a ring flip. Axial and anti-periplanar, meaning the leaving group is up and then the proton is going to be down, or the other way around.
But the living group's always going to be axial.
They have to be in order to eliminate.
Okay, perfect. Okay.
Yeah. So now my position 1 is here. 1, 2, 3, 4, 5, and 6. So my chlorine, in this case, it's 1 and up. So is it going to be axial or equatorial? Axial. Okay. My methyl is in position 2 and it's down, so it's going to be axial or equatorial? Axial. Okay. So now we said the leaving group and the proton, they have to be anti-periplanar, which means they both have to be axial, and one has to be up and one has to be down. My chlorine here is axial up. Do I have a beta proton in this case that's axial down? So will I be able to deprotonate carbon 2? No? So which one do I have to use? Carbon 6, the proton that's on carbon 6, because I have a proton that is axial down, and that means that they are anti-periplanar.
And you
Yep.
can't use the methyl because
Methyl you don't eliminate
You're anti-paraplane with what?
with the proton,
What's anti-paraplane?
the leaving group and the proton.
Oh,
Because remember, we're doing an elimination. In an elimination, we have the leaving group that leaves, and then a base deprotonates the beta proton.
what's rule for E1 and E2 or just
E2.
E2? Just E2?
Did you have a question?
Yes. So because we can number however we want, there's a situation where we might not have to do a ring flip because we possibly
Right, exactly. In this case, we had to do a ring flick just the way that we numbered it. But if we had started one and another, and like the chlorine was already axial, you wouldn't have had to do a ring flip. Good question.
Oh, we had to do a ring flip because the CL wasn't axial, right?
Right, the CL was in an equatorial position. Yep.
so the H we're going to use is going to be axial down.
Yeah, right here, you see, on position 6. We can use this H. Why can't we not use the H on carbon 2? It's up and it's in what position? Equatorial. We can't do that. My proton and my leaving group have to be anti-periplanar to each other.
And the reason is just for them to not.
It's how they overlap. Exactly. Yep.
Already two H's on number 6 anyway, but we're going to use one that's axial down.
Yes, exactly. Good point. So we have two H's here. We have an axial down and an equatorial up. Which one are we going to use for the elimination? Axial down. This one and this chlorine. So now this leaves, something deprotonates this, and I'm going to form a bond between 1 and 6. So now if I come back to here, right? Same numbering. 1, 2, 3, 4, 5, 6. I have a methyl that was on a dash, so that's going to stay the same. Where's my double bond again? Between 1 and what? So my double bond is going to be here. So now if we go back and look, oh wait, this is right here. Which one is that? E?
So the methyl stays the same configuration.
Why?
It wasn't being eliminated.
It didn't participate in the reaction, it's just there. Good question. Okay. So 84 is going to be the same thing. You're going to have to do a chair conformation. It's E, which is both C and D, I think. I'll post it up and I'll put the correct answer. Do you guys want me to drive for you? I can. It's just that there's still like a lot of questions to go through, and we just did one like it. So it's good practice. Do you guys want me to drive for you? No? Move on? All right. All right. 85. What are the steps in the following mechanism in the correct order? I heard C. Why? What's happening? Proton transfer, okay. What are we doing a proton transfer? Make it a good leaving group, okay. Okay, so the OH is going to leave. So we can do this, and this one's out, and this one's out. So proton transfer, loss of a leaving group, then what? Rearrangement. And then a proton transfer. Awesome. E. So, does anybody need me to draw the mechanism? Do you guys get this mechanism? Everybody good? Okay. 86. And again, guys, if we don't get to finish it, that's okay. I am going to post the answers, okay? Which of the following is a... Huh? It's dehydration. Because the water is leaving. Yep. Which of the following is a structure? I would know that, by the way. Like, remember, this is how you form a double bond when, like, you have an OH. Professors love that reaction. They really do. Which of the following is the structure? But you guys pretty much have to know everything, so never mind. Which of the following is the structure of the rearranged carbocation in the following dehydration? So again, what's happening? The first step that happens in this reaction, what is it? Proton transfer. So that makes this a good leaving group. Now what? Loss of leaving group. So this is going to leave. So you have a carbocation here. So you guys said what? Okay, so what answer is it? B. So I'm going to move this methyl over here. And now my carbocation is here. Everybody good? So how come we did a rearrangement? To go from a secondary carbocation to a tertiary, which is more stable. Cool. Yeah. Yeah, that's a good point. This one we could have eliminated like off the bat because the carbon has 4 bonds. So will it have a positive charge if it has 4 bonds? So that one's out. All right. This is the same thing as this. That's not even rearranged. And that, I don't even know what that is. That's out. All right. So the expected Markovnikov addition product of HI to 2-methyl-2-butene is... So what is the first step that you're going to do here? What should you do? Draw it out. Okay. So it's a butene. My double bond is in 2. And I have a methyl at 2.
The halogen goes to the more substitute carbon, and the hydrogen goes to the less substitute.
Cool. Why? What is that called? Markovnikov rule. Awesome. Okay. So we said we're going to add HI. Right? And we said the halogen, in this case, is Markovnikov. So that means that my group is going to go to the more substituted. Oops. I. That's an I. And there's an H here. So what is that, guys? D. All right. Everybody good with that one? You guys should be should feel comfortable about going especially with the naming. Especially for the people that are going to Orgo 2, the ACS loves these kind of questions. Where it's like they give you a name, they give you the name of the reaction, you do the reaction, and then you name that again. So get comfortable with this, yeah.
I don't want to confuse anybody by asking this question.
That's okay.
Would the I ever go to the butane because I is a good lead group? Is that just kind of irrelevant? They just want to know where you put the I in relation to Markovnikov, but I would never go in there because I is a lead group.
Say that one more time because I got a little lost.
Iodine is a really good leading group.
Okay.
So would it ever attach to a butene?
What do you mean, attached to a butene? Oh, you mean if you have this, can you do more reactions? Like where it leaves, like an SN1 or an E1?
Kind of, but my only question is why would I, in like a science sense, why would I attach to that molecule with the double bond? Why would it do that?
Because it's part of the reaction. Yeah, because you have addition. You're having a nucleophilic attack. You have the I with the hydrogen. So this is just like any other reaction, right? The properties of whatever you have. You know, if you have sodium methoxide, so like Naomi, right? That's what I call it. And if you have it with a tertiary substrate, you're more than likely going to do an E2, as opposed to like if you have a primary, you're going to do an SN2. It just depends on the conditions of the reactions that you have. Does that make sense? But that was a good question. Okay. 88. Did you guys, who got to the radicals chapter in you guys' class? You guys got to it? Okay, cool, so let's do it. So what is the expected major product for the following reaction? D. Why? Right, awesome. So we have HBr, but because we have the peroxides, it's an anti-Markovnikov addition. Everybody good with that?
What if it was CL?
Same thing.
Same thing. They said something like it was CL, but there's one where
You're thinking about when you're
NBS or
halogenating an alkane. Like if you have Cl2 and Br2 with light or heat, or yeah, the Cl is going to react differently than Br2. It's not the same as this one. That's only when like you're reacting that with an alkane. And then like when you're doing it with a Cl, you can end up halogenating more than you want to. But we're not going to get into that right now. All right, so 89. Which of the following alkenes below would be expected to produce a chirality center upon hydrohalogenation in the presence of peroxide? D? B? Okay. Everybody agree? Why? Okay, right? So we said hydrohalogenation, so it can be HBr or HCl, it doesn't matter. But we're doing it with peroxides. So where is my halogen going to go to? The least substituted. Awesome. So if it goes to the least substituted, right? Let's just do BR. Okay. Do I have chiral centers now? Yeah? Okay, cool. Let's do C. Here, we'll add it here. You have any chiral centers? Okay. Say that one more time.
It's because for the other answers you can't find a more substituted carbon.
The other ones,
B, you know which ones.
I mean, C, you have one that like, you have a more substituted and a less substituted. But when you add the BR to the less substituted, you don't form a chiral center.
Oh, right.
Yeah, because what we're looking for is a chiral center, right? Okay. So 90. Treatment of S6-chloro, 1-methyl, 1-cyclohexene with H3O is expected to produce which of the following? So what is the first thing that you guys have to do? Throw it out. Awesome. So cyclohexene, right? And I have a 1-methyl at position 1. And I have a 6-chloro, so 1, 2, 3, 4, 5, 6. And then it says it's S. So is it going to be on a wedge or a dash? All right. So now it's telling me that this is going to react with H3O. So what kind of reaction is that? Hydration? And we're using a what? What is this? An acid? So it's acid catalyzed hydration. All right, so what is the rule for this reaction? Oops. The OH is going to go to the most substituted. So Markovnikov, awesome. mark. Okay. So what is this mechanism look like? What's the first thing that happens? The double bond attacks hydrogen, and then the electrons get left behind, right? So do I form a carbocation here? So where does my H go? To the least substituted. So what happens to this carbon over here? So I have a proton. Yeah? So just remember for this one, like it's important to remember that you can have a rearrangement if it's possible to like do a rearrangement. Okay? That's why I just went into the mechanism of it. All right? So now what's going to happen? OH what? The carbocation? The H2O? And then we deprotonate it with the water. Cool. So which one is that one, guys? B? Everybody good with it? Yes? All right. Afterwards you can, yeah. What is what? Okay, good question. So we form a carbocation. So when we form a carbocation, how can it get attacked? With a carbocation. Is it backside or front side? Or both? Both, right? Yeah. It just didn't have the option of enantiomer. But in reality, does this one have an enantiomer for an answer?
Yes.
Why?
Because it's got either front side or back side.
Exactly. Awesome. Carbocations are planar, right? So when we do the nucleophilic attack, they can get attacked from both sides. But now, just a thing to add to this, if you do the front and the back-sided attack, in order to have an enantiomer for an answer, what do you need to have? A chiral center. If you don't have a chiral center in your answer, can you have an enantiomer? Awesome. All right. Yes. So what is the expected major product for the following reaction? This is oxymercuration, demercuration, but you're going to end up adding also an ethyl group. Because you're not just doing it with water, you're doing with a... Okay, Markovnikov. Okay. Right, this tells you that this reaction is a Markovnikov addition. So which one is out, guys? E is out. Why is E out? Right, exactly. When you do the nucleophilic attack with this, you're going to add the ethyl and the oxygen, not just an OH. Now, if it was H2O, what would you add? Oh, an OH. Awesome.
So is anytime that OH is attached to like a carbon group?
It's gonna take it with it. That's a good question. Yeah. Okay. So I don't know where that carboxylic acid came from. Good job. So which one, guys? So let's start drawing it out. So we said that this alkene is going to go away, and we're going to add an OET to the most substituted side. So which one looks like that? You sure? So a good way, and this is why I say always number your carbons. Because when you number your carbons and you number them in the same way, it's a little easier to see than just doing it by eye. So let's start numbering here. 1, 2, 3, 4, 5. Right? Huh? We're not naming. It's just for your purposes to know, like, that you're getting the right amount of, like, carbons, and, like, that you're doing it correctly. Yeah.
You only have 2 carbons to choose from, so it's C.
It's C? Okay. So let's number it, right? So on this side, I started from here. So I go 1, 2, 3. This is my 4, which makes sense. But if you see, in this, it's just flipped. My ether group is at the bottom. In this case, it's pointing up. So that's why it's helpful to number it, just so you can see it a little bit better. Does that make sense?
So does A have too many, or why isn't it? Like, I'm confused how it works.
We can look at it. Yeah.
What did the second reaction do?
Good question. I think it oxidizes it. But did they go into the mechanism of this reaction? Yeah. I'm not.
It's just one of those things where it's like the next question where we just know based on the bottom what the product.
It's like both reactants. To be honest, like, I would tell you if I remembered exactly what it did. You should know, because, like, they could ask you something like that, but it's part of, like, the same reaction. Like, something that could help you when you're doing reaction is, like, recognizing, even though it's 2 separate reactions, which ones go together. So in this case, they all go together. Mm-hmm. Okay. Actually, this is a reducing agent, so maybe reduces it. I'm not sure. Yeah. Right? Yeah. NaBH4, sodium borohydride, is a reducing agent. That's a good question, though. It's probably in your book. Yeah. So why is it not A? So let's count. So this is 1, 2, 3, and 4, right? But if you guys notice, when we looked it up here, my ether was coming off of carbon 4. And in this case, it's not. It just keeps going on. Does that make sense? Good. Yeah, that's anti. Does that make sense, guys? All right, cool. So if you guys don't remember anything that I say today, what is the one thing that you guys should remember that's got to stick to you?
If you have a beta carbon,
That's one, but I feel like it's the most important one. Always count your carbons. Right? Yeah, count your carbons every single time, guys. It's gonna, like, avoid mistakes. All right. What is the expected major product for the following reaction sequence? So this is BH3, THF, H2O2. Oh, I think this is the one that oxidizes the second step. So I think the first one it reduces. Not sure. Look in your book. I'm probably going to check now because it's killing me to know. What? Hydroboration oxidation. So what happens in that reaction? Anti-Markovnikov of what?
OH. OH goes on the
Anti-Markovnikov of addition of OH. Awesome. All right. So anti-Mark. And then we're going to add OH and an H. Okay. So which one looks like that? C? You sure? E? Okay, let's talk about it. What? So if we have an alkene, right? We say it's anti-Mark, but anti-Mark has to do with what? Addition, yeah, but, like, what does it say? What is the rule, like, Markovnikov or anti-Markovnikov? More substituted or less substituted, right? So we know in this case, my OH is going to go here. Awesome. It's syn addition, yes. So we're adding it in syn, the OH and the H. So that means that when I attack this alkene, both my OH and my H are either going to come in as a wedge, or both of them are going to come in as dashes. Does that make sense, guys? So in this case, if I do my OH as a wedge, what does my H have to be? Wedge. So if my H is a wedge, what does my ethyl group have to be? A dash. So which one is that? E. Awesome.
but plus an antimer, doesn't that just make this? Oh, then this will be.
Exactly.
Okay.
Mm-hmm. Yeah. But you're adding the H, not the methyl.
The H is the one that is
And needs to be in the
Wait,
back.
what are we comparing? Which two?
the H and the OH.
The H and the OH.
Oh, because that would make the ethyl a dash. Because the
A
hydrogen
wedge.
is a wedge. Because the
Oh,
hydrogen
yeah, yeah, yeah.
is a wedge.
Yeah, yeah, exactly. Exactly. Don't let it confuse. Like, when I first started learning this used to confuse me because I used to say, oh, it's syn because they're both in a wedge. But the methyl was already there. That's not what we're adding. What we're adding is the H. So both the OH and the H get added as a wedge or as a
C
dash.
would be,
Anti.
yeah, anti, yeah.
Because in chain, we have, so the second part of the reaction underneath the line would determine anti or syn, right?
Say that one more time.
On the second reaction, this whole thing would determine whether it's anti or syn.
No, this reaction is just syn.
But like, there's another situation where the answer would be an anti, correct?
For this particular reaction, oh, you're thinking about oxidation when you're doing, when you're adding two OHs. Yes, okay, yeah. Yes, exactly. I think there's examples of that, so hopefully we'll get to it. All right, so this is just like, it's talking about the same thing. It's actually 12:33, guys. I'm so sorry. I wasn't looking at the time. I went over. So, like I said, I will post the questions up, the answers. Thank you so much for coming. Yeah.
It's just 91. I know you were saying that when we have AG something else, we add everything that it's containing the OH, and when it's water, it's just OH.
Yes.
What's the reason for that?
Because when you add it, you're gonna add it like, can I write on there?
Of course.
So like when you add it, like, you just do it quickly, right? It's an alkene.